Hello, I'd like to discuss a little mathematical problem that I found very interesting. I was working on with my grandson Charlie recently. Um, we were doing a problem concerning how many lines can be made out of an array, a linear array of n line segments. For example, this is an array of 6 line segments. How many lines can be made out of it? Well, we can make uh, unit line segments, 1, Unit 2, Unit 3, Unit 4, Unit 5, Unit 6, and that's so there's 6 ones. But we could also make segments out of lines out of 2 segments, 1 plus 2, 2 plus 3, 3 plus 4, 4 plus 5, 5 plus 6. So there's 5 2s, and if you went on, you'd see that there's 4 3s, 3 4s, 2 5s, and 1 6. So for a 6 segment line, you could make up 21 different lines with lengths of unity, 2, 3, 4, 5, 6. And by the way, if you went from 6 to 7, you'd see that it was 7 plus 6 plus 5 plus 4 plus 3 plus 2. So each time you increase the segment by 1, the line by 1 segment, the number of lines you can create increased by the new number. So well, before we go on, after we complete this one-dimensional problem, we're going to discuss a two-dimensional problem. How many rectangles can we create out of an n by n array? In this case, it's 2 by 2 array of rectangles. How many cuboids can be created by an n by n by n array? Or in this case, it's 2 by 2 by 2. So we'll talk about that after we finish the one-dimensional problem. And then we also want to see how these different problems are related to one another mathematically. So for the one-dimensional problem, if you have an array of 0 segments, you're only going to be able to create 0 lines. If you have an array of 1 segment, you'll create 1 line. If you have an array of 2 segments, you'll create 1, 2, 3 lines. With 3, it's 1, 2, 3, 4, 5, 6. You notice it increases when you go from 2 to 3, it increases by 3. And when you go from 3 to 4, it increases by 4. All right, here's the 4. You have the individual units, the 2 units, the 3 units, and the 4 unit. That gives you a total of 10, 15, and so forth. So let's look at the mathematics. I used Excel to look at the number of segments in the line and the number of lines that can be created. I plotted y versus x using Excel. And I used Excel to determine the equation for the line using a polynomial of order 2. We get a perfect fit. Y equals 0.5x squared plus 0.5x. The correlation coefficient of 1 indicates that it's a perfect fit. So now let's go to the two-dimensional problem. So in a two-dimensional problem, if we have an n by n array, here we have a 3 by 3 array, x by x, or n by n. How many rectangles can we create out of this array? And of course, we can create, for this, let me go through this example in detail. We have the unit rectangles, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 ones. You can show that there's 12 twos. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You'll easily be able to show that there's 6 threes, 4 fours, 4 sixes, and 1 9 to give you a total of 36. And by the way, that number 36 is 6 squared because it turns out that it's the square of the one-dimensional problem. So we'd like to go through this problem with arrays from 0, 0 by 0, 1 by 1, 2 by 2, 3 by 3, 4 by 4, 5 by 5, etc. And we want to know what the mathematical relationship is between the number of rectangles that can be created and the order of the array. So this particular array is order 3. It's a 3 by 3. All right, so if we had a 0 by 0 array, of course, you couldn't create any rectangles. A 1 by 1, you could create 1 rectangle. 2 by 2, you can see that you can create 9. You have 4 ones. You have 3 twos. 1, 2, I'm sorry, 4 twos, 3, 4 twos, and 1 4, total of 9. For the 3 by 3, it comes out to be 36. I've already worked this one out. And by a 4 by 4, it's 100. I've shown for the ones there are a total of 16. For the twos, there's a total of 24. For the threes, there's a total of 16. For the fours, there's a total of 8. For the fours and a block, there's a total of 9. For the sixes, there's a total of 12. For the eights, a total of 6. Nines, 3s, 4. 12s, 4. 16, 1, for a total of 100. Okay, so let's look at the mathematics of this two-dimensional problem. So I have the number of the order of the array, 0 by 0, 1 by 1, 2 by 2, and the number of rectangles that can create it on the y-axis. And when I plot it, I get 0.5, y equals 0.5 x squared plus 0.25 x to the fourth, I should say, plus 0.5 x cubed plus 0.25 x squared, and that is the square of the solution to the one-dimensional problem. And each of these numbers is actually the square of the one-dimensional problem. Now the 3 by 3 problem is a little more complicated, and let's look at 4 different three-dimensional arrays: a 1 by 1, a 2 by 2, 3 by 3, and a 4 by 4. We're only going to analyze 0, 1, and 2, and then we'll generalize to 3 and 4. So if we have a 0 by 0 array, of course, we can only create 0, 1 by 1, only 1. If you look at the 2 by 2 array, if you look at the individual cuboids, there'd be 8, 4 on top, 4 on the bottom. If you look at the twos, well, let's look at the top. 1, 2, 3, 4 on the top, 4 on the bottom, and then if you go up and down, that's 4 and 4, 8, 9, 10, 11, 12. So there's 12 twos. The number of fours, well, each face has 4, so there's 6 faces with 4 in each. So there's 6 fours and 1 8. If you add that together, that's 27. Now, if you compare that to the one-dimensional problem, the number of lines that can be created by a 2-segment was 3, and 27 is 3 to the 3rd power. So in analyzing the 3-dimensional problem, I'm not going to try and do the 3 by 3. I'm going to assume that the solution to the 3-dimensional problem is the cube of the one-dimensional problem. So 1 squared, 0 squared, 0 cubed, 1 cubed, 3. I'm on the 2-dimensional, excuse me. Let's go to the 3-dimensional problem. 0 cubed, 1 cubed is 1, 3 cubed is 27, 6 cubed is 216, 10 cubed is 1,000, etc. And when you look at the mathematics of it, Excel will show you that y is equal to 0.125 x to the 6th plus 0.375 x to the 5th plus 0.375 x to the 4th plus 0.125 x to the 3rd. And this is the cube of the one-dimensional problem, which I have shown here. Here's the one-dimensional solution. If we square it, we get the two-dimensional solution. If we take the two-dimensional solution times the one-dimensional solution, we get the three-dimensional solution. Okay, now you can even generalize this to a four-dimensional problem by just taking the results for the one-dimensional problem and raise it to the 4th power, and you get this equation, which is the 4th power of the one-dimensional problem. This would be, of course, hypothetical because we don't have 4 spatial dimensions. So I hope that you've enjoyed this little problem. It's a good example of picturing things in 1, 2, and 3 dimensions, and using spreadsheets to analyze numbers and to get equations. And I think it's a good learning exercise for students at various levels of education. So thank you for your attention, and I'll look forward to seeing you next time.